Okay, in this video I'm going to talk about fractional colorings and the fractional chromatic number of graphs. So basically this is a generalization of the proper colorings of graphs and just the regular chromatic number of graphs. So like it's a way to define colorings in fractional number of colors. So like it's not like we cannot literally use fractional number of colors. Let's say 2.5 colors. We cannot literally use 2.5 colors, but by the end of this video, like you will see how to define some notion of this fractional colorings that would, in a sense, represent a coloring in fractional number of colors. So like in particular, I will show you like a specific graph and a specific coloring that in a way would mean like coloring in 2.5 colors of this graph. So yeah, so let's first remind the definition of the proper coloring. So a proper coloring, basically it's a it's an assignment. So it's a function C that maps the vertices of the graph to a number of colors. So let's say to a set of colors, let's say from 1 to k, let's say, where k is the number of colors, such that if two vertices are adjacent, so if the vertex u and v are adjacent in the graph, then c of u is not equal to c of v. So that's the condition. So basically the vertices that are adjacent in the graph, they cannot be colored in the same color. So this is prohibited. That's the proper coloring. So now the fractional coloring would be a function that maps the vertices of the graph not to numbers, so basically we assign to each vertex not a single color but multiple colors. So we introduce two parameters a and b, and we say that the fractional coloring with parameters a and b. So each vertex gets a set maps, well, I will write in words, so maps to sets of b colors, and a is the total number of colors. So b is the number of colors that each vertex gets. Each vertex gets, and the a is the total number of colors. Okay, so each vertex basically gets a set of colors, so b colors. So let's have an example. We have a graph, and let's say this vertex gets colors 1, 2. This vertex gets colors 2, 3. And this vertex gets colors 3, 1. Let's say this. So this is not a valid coloring, because yeah, so like I didn't yet state the condition, and the condition, like similar to this one for the proper coloring, is that the sets, if the if the vertices u and v are adjacent, then the sets u and v, the sets c of u and c of v are disjoint. So like this. So here in this example, we have basically the set of colors 1 and 2, and here we have the set of 2 and 3. So they're not disjoint. So the color 2 repeats here and here. The color 2 is in common for these two vertices, therefore this is prohibited. So this coloring is not a valid fractional coloring. So let's write the formal definition. So this is kind of so a fractional coloring of graph G is an assignment of a set of B fractional coloring with parameters. Yeah, so let's write this fractional A colon B coloring. A colon B coloring of graph G. So A colon B, so like we have the parameters A and B, and this notation is intended to remind like it's kind of A divided by B. So like it's not exactly A divided by B, but like we introduced this notation. So like it would be like kind of a coloring in A over B colors. So like it's informally. So this is approximately equal to A. So approximately equal to coloring in A over B colors, right? So like we cannot literally color in A over B colors, but this is like a formal definition that like in a sense would mean coloring in A over B colors. Okay, so and therefore this notation A colon B. So A colon B coloring of graph G, where A and B are natural numbers, it's parameters. So is an assignment of a set of B colors to each vertex of graph G of G. So each vertex receives the same number of colors, B colors, a set of B colors. Set of B colors to each vertex of G, where while A where A is the total number of colors, or let's say out of, so the set of B colors to each vertex out of the total of A colors, out of the total of A colors. So in total we have A colors, and each vertex receives B color. So for example, like in this example, even though it's not a valid fractional coloring, but like in total we have 3 colors, 1, 2, 3, and each vertex receives 2 colors. Each vertex receives a set of 2 colors. Out of total of 8 colors, such that, so this is an assignment such that for any 2 adjacent vertices, their sets of colors are disjoint. Their sets of colors are disjoint. Yeah, so that's the full definition. So a color is prohibited to appear at the end of an edge. So like if we have an edge in a graph, then the same color cannot appear in the set. So it's one something and here one something. So this is prohibited. These 2 sets must be disjoint at the end of any edge in the graph. So now let's write another definition. So a graph is A colon B colorable. This is kind of an obvious definition, but let's write it. A graph is A colon B colorable if there exists an A colon B fractional A colon B coloring. Like it's, yeah, like the word fractional, like it can be sometimes omitted. So like we can say fractional A colon B coloring or just A colon B coloring. When we say the parameters A colon B, like it's also like it's already clear that we are talking about a fractional coloring. So the word fractional sometimes we will omit. An A colon B coloring of this graph. Yeah, so it's A colon B colorable if there exists an A colon B coloring of this graph. So it's like with parameters A, B. So it's kind of an obvious definition. And finally, we define a chromatic number. So the fractional chromatic number of graph G denoted by he with index f of G is the infimum over all parameters A, B, such that the graph G is all parameters A, B such that G is A colon B colorable. So all of this is under infimum. So AB such that G is AB colorable, infimum of what? Infimum of this fraction A over B. So A divided by B. And this is where like the A divided by B appears explicitly. So like we actually do divide A by B somewhere, like, and it's here. So the infimum of all such fractions A divided by B such that A and B are parameters of a fractional AB A colon B coloring of the graph G. So this is called the fractional chromatic number of a graph. So notice that this is not necessarily an integer or a natural number. Like it can be really a fractional number. So like it could be 2.5 or whatever. Like, yeah. So let's. So let's write this. A fractional chromatic number is not necessarily a natural number. It can be a fractional number. So and this is where like it's a sense in which we color a graph in a fractional number of colors, because the regular, so remind that the regular chromatic number of G is the minimum number of colors. So it's defined as the minimum let's write it like minimum of A, like to keep the same notation as here. So A is the total. So in the fractional, because in the fractional coloring, A is denoted as the total number of colors. So here we have like denote the same by the same letter A. So where G is A minimum over all A, such that G is A colorable. Yeah, so the regular chromatic number is the minimum. Basically, it's the minimum number of colors in which we can properly color the graph, right? So it's a minimum over the total number of colors, such that we can color G in A colors. So that's basically what it says. Minimum number of colors in which we can properly color the graph. Now, the fractional chromatic number now is the infimum of A over B, such that it is A colon B colorable. So in a way, it is some number such that graph is colorable in this fractionally with these parameters A and B, and so in a sense, informally, this fractional chromatic number of G is the is the fractional fractional number of colors is the minimum for like is the minimum fractional, not minimum but like infimum of yeah, like if we're talking informally, let it be minimum, but because this is informal, this is not a formal definition. Informally, so this is the minimum fractional number of colors. Number of colors in which we can color G. So yeah, so like informally, if we consider like I said here, that informally the fractional a colon b coloring, it can be considered as a coloring in a over b colors. So in this sense, it is the infimum of this number of colors. So this definition basically says that it is the infimum of the number of colors in which we can color the graph fractionally. Yeah, so infimum of the fractional number of numbers of colors in which we can color G. Yeah, so now let's first consider some property and the connection with the regular chromatic number, right? So first we notice that in the definition, so let's write again the infimum so the fractional number of G, fractional chromatic number of G is equal to the infimum over of all AB of A over B, minimum such that G is A colon B colorable. So we notice that we can set, so since it's an infimum over all values of A and B, we can set B to 1. So if you can set B equal to 1, then this then basically, so we consider a set of parameters A such that and B equal to 1 such that G is A, so A colon 1 colorable. It's the same actually as just regular coloring, as just A colorable, proper A colorable, right? Because remember B, the parameter B is the number of colors that each vertex receives. So if each vertex now receives only one color, this is just a regular proper coloring. So, all right, so the regular proper colorings, they are included actually in this infimum, in these parameters AB, because B is equal to 1 is exactly proper colorings. So since it is a subset, so the subset of all possible parameters, therefore the infimum, so this would be less or equal than the minimum by all A of A over 1, or let's write infimum first. infimum by all A such that G is A colon 1 colorable and this is exactly equal, this infimum exactly equal to minimum over all A such that G is A colorable. Minimum of A, and this is just equal to regular chromatic number of G. So basically what we established is that the fractional chromatic number of G is less or equal than the regular chromatic number of G. Right, so and again, this is a natural number. Chromatic number of G is the minimum number of colors, so this is a natural number, and this is not necessarily a natural number. It can be like a rational number. So now I will give an example where this inequality is strict, where we don't have inequality. So to prove that this is a meaningful definition that is different from just regular chromatic numbers, I will show an example of a graph that where the fractional chromatic number of this graph is strictly less than the regular chromatic number of graphs. So the graph is a cycle on 5 vertices. It's denoted C5. And first, let's find the regular chromatic number of this graph. So, like, it's easy to see that we can color it in 3 colors. So we color, and just any cycle we can color in 3 colors. So first we color and we alternate the colors until the last vertex. So we go counterclockwise, right? So we color 1, 2, 1, 2, and the last vertex we can color neither 1 nor 2 because it's adjacent to the vertices of both colors. So we use the third color. So this is how it's colored in 3 colors properly, and it's easy to see that we cannot color it in 2 colors because it's an odd cycle, a cycle of odd length, and it's not bipartite. So like there was a theorem, like I made a separate video about this, that bipartite graphs can be characterized as the graphs that don't contain cycles of odd length, don't contain odd cycles, and so this is itself an odd cycle, so it is not bipartite, and bipartite graphs are exactly 2 colorable graphs, so that can be colored in 2 colors. So therefore, since it's not bipartite, it cannot be colored in 2 colors, but it can in 3 colors. So the chromatic number of C5 is exactly 3. And we can see kind of informally that the third color is like it's only used for the last vertex, right? So we can, so informally we can see that we can color most of the graph in 2 colors. We can color the most of C5, the most of the graph C5 in 2 colors, and the third color is needed only for the last vertex. The third color is kind of the last resort, and the third color the third is needed only for the last vertex. So informally we kind of see that yes, it's the chromatic number is 3, but it's kind of closer to 2. So kind of most of the graph is 2 colorable, but only the last vertex requires the third color. So informally we kind of see that the number of colors required is really not like it should be less than 3. So, and this fractional chromatic number kind of demonstrates makes this formal. So first from this coloring, so let's I will repeat it again. So if we take this same coloring in 3 colors, 1, 2, 1, 2, 3, so we can obtain from it so this is kind of proper coloring, and also like 3-1 coloring, fractional 3-1 coloring. So when each vertex receives 1 color, and in total we have 3 colors, so we can obtain from this 6-2 colorings, this 6-2 coloring, by splitting each color into 2. So basically we split color 1 into 1-4, so 1-4, this vertex also 1-4. Now the color 2 is split into 2-5, 2-5, and the color 3 we split into 3-6, right? So, and it's easy to see that this is a 6:2 coloring. So each vertex receives 2 colors, and in total we have 6 colors, and like every the ends of every edge get disjoint sets of colors. So no color is present at the both ends of any edge. So by splitting each color into 2, we can obtain easily these 6-2 colors. But when we consider this, the parameter b equal to 2, when each vertex gets 2 colors, it's actually like 6 colors is actually not the minimum. So we can I will show how to color with 5 colors. So 5 colors would be enough. So and this would be a 5:2 coloring. So let's so 1, 2, and 1, 2, 1, 3, one, 3, 3, 4, 4, 5, and here 2, 5. Yeah, so like we can directly check that no color appears at both ends of any edge, so that any edge connects only disjoint sets of colors, and so we use only 5 colors where each vertex receives 2 colors. So this is a 5 colon 2 coloring, fractional coloring, and this so like again, so we see that when we use this 6 colon 2 coloring, like most of the graph is colored into this 1 4 to 5 1 4 to 5. So we use only the colors, the colors from the colors 1 2 1 2 4 5. So only 4 colors, and the last two colors 3 and 6 are used only for the last vertex. So most of the graphs is colored into 4 colors, and the last two colors are used only for one last vertex. And so here we kind of use it more, we distribute the colors more uniformly, but we use less colors. So instead of 6 we use only 5 colors, but we use them more uniformly. So the fact that we have 2 colors on each vertex, it permits us to use less colors, like rather than in the case here when we have only 1 color in each vertex. So yeah, so we use, so basically this example shows that the fractional chromatic number of C5 of the graph of the cycle on 5 vertices is less or equal than 5 over 2, then 2 and a half. 2 and a half, which is strictly less than 3, which is the chromatic number of C5. Yeah, so for this graph C5, the fractional chromatic number, like I didn't prove what it is exactly. Like it might be 2 and a half, it might be less, but this example shows that is less or equal than 2 and a half. But we showed that it is strictly less than the regular chromatic number of C5. So for all graphs, it's less or equal than chromatic number, and here is an example where it is strictly less than the chromatic number. Yeah, so that's it for this video.